Okay, good evening. Tutorial number 7.
Will we solve analytically those equations?
No. Okay, so this tutorial we are going to continue talking about two-dimensional bifurcations. In two-dimensional, what we have is like we can look at this as we have two axes. Okay, one is the axis of where the bifurcation appear. Okay, and the other one is the switch between the two types. Yes.
אני מצטער על השאלה, אבל המקרן פה הוא נראה לי קל. אם כבר אין הקלטה אפשר בעברית אולי?
יש מקרן, יש לך.
No, there are student papers.
לא, אבל אין הקלטה, לא?
Okay, I'm sorry. Yeah.
ביוטיוב לייב.
Okay, so let's start to talk about Hobbes bifurcation. Okay, let's look at the following system. We have r dot is mu r minus r third and theta dot constant. Okay, let's look how this function f of r mu r minus r3, how it depends on mu. We have r and mu. And for mu lower than 0 here, the function looks like this. Okay, that means we have stable point here. When mu equals 0, we have similar but in some different shape. Okay, and for mu bigger than 0, we have this thing. Okay, that means here we have a stable point and here an unstable point. Okay. So how it looks like for mu lower or equal to 0, we have some spiral, okay, that's going into the point r equals 0, okay. And when mu is bigger, we have r equals 0, and we have another circle right for this point, and we have inside we have an unstable, like the r equals 0 is unstable and this r is stable. Okay. Okay, so we can see that we have a bifurcation, right, for this point. So how the diagram looks like, we have r and we have mu. I'm sorry, this is mu and this is r, and we have for mu lower than 0, we have stable right on r and unstable 0, and the diagram looks like this. Okay, how it looks like. It is very similar to pitchfork bifurcation, right?
With only one pitch.
Yes, it's a pitchfork in the yes, r-axis, because r cannot be.
It is not good for A.
What do you mean?
כאילו חציר בשביל...
Yeah, no.
זה היה ממש לא מצחיק בהרצאה, וזה עכשיו עוד יותר.
אני מחזר בדיחות.
כן.
Okay.
צחק.
מאי נוחות.
That's what more fun. And I don't laugh, I smile.
זה יבן שני לתרגיל
אוקיי.
הבית, אם את רוצה. זה יבן שני לתרגיל הבית, אם את רוצה. הוא הראה לעצמה ברגל, כתוב שהם למדור אותה.
Okay. Let's look on the eigenvalues. Okay, for that let's move to Cartesian coordinates. Okay, we have x dot is r. Okay, I hope it will work until the end of the tutorial. R cosine theta and y is r sine theta. Okay, so x dot is r dot cosine theta plus theta minus theta dot r sine theta, and y dot r dot sine plus theta dot r cosine theta. Okay, what does it mean? X dot is r dot is mu r minus r3 cosine, cosine theta minus theta dot is omega r sine. This is actually mu minus r squared r cosine theta minus omega r sine. Okay, this is mu minus x squared minus y squared, right? Dot times x minus omega y. Okay, in the same way, y will be it will be mu y minus yx squared plus y squared plus xw. Okay, the Jacobian is mu minus omega mu, and therefore the eigenvalues are omega plus minus I omega. Mu, I'm sorry, plus minus I omega. Okay, so what can we say? First, we have an imaginary part. Okay. Second, we can say that where mu cross the imaginary part actually from minus to plus, that it changed the type of stability, and this is what's the word? Like the regular situation for Hopf bifurcation. Okay? Okay, cool.
איך הקוביין יצא לך, כאילו, מה עם החלק של x בריבוע?
We are looking at the origin. Okay, this was a supercritical, okay, of bifurcation, and now the subcritical. So let's look on the system. R dot is now mu r plus r third, and theta dot is still constant. Okay, so for now we have if mu lower than 0, we have f in r. We have this, okay, unstable. Stable for mu equal 0. We have this, and for mu bigger, we have this. Okay, so for now, the diagram is we have stable and unstable circle. Okay. And an unstable spiral. Okay? Let's again look at the, I'm sorry, first. No, wait. Yes, okay. So this is now the situation, and the diagram will be just the opposite. We are stable where mu and r. Okay, where mu is lower than 0, r equals 0 is stable, and after it became unstable, and we have the unstable r here. Okay. Ta-da-da-da-da.
This is the last diagram. When the mu biggest than 0? I don't understand.
Where mu is bigger than 0,
Okay.
we have just one critical point. Okay. The eigenvalues, we can do the same with a process, but at the end we will get the same Jacobian, right? Because the squared part will be 0. Okay, this is the change with the plus or minus. Okay, so we can see that we will have the same eigenvalues, and therefore the eigenvalues cannot tell us the type of the Hopf bifurcation, right? But it just tells us that there is. Okay? Okay, exercise. Consider the system x dot is y minus 2x and y dot is mu plus x squared minus 1. A. Sketch the outlines. B. Find
Fair enough.
and classify the bifurcations that occur as we and C. Sketch the base portrait and function of u. Okay. Okay, so let's start. A. Sketch the outlines. So what are the outlines? Where x dot equals 0 or y dot equals 0, right? So this time x dot equals 0, this is the line y equal to x, and this is y equal mu plus x squared, right? So we have for mu. Okay, for mu lower than 1, we have, okay, so let's look at this. X and y, we have this and this. Okay, this will be, yes, this. For mu equal 1. We have 1 cross point, okay, to go over here. And for mu lower than 1, we have just this and this. Okay? Okay.
Next week we will talk about chaos. We will start, or today we will start.
I don't remember. No, today not. But I don't remember. Next week.
Okay.
Okay, define and classify the bifurcation. So what bifurcation we see that we have? No.
Saddle.
Great, I don't know. We have
Yeah, 0 to 2.
yes. Great. There.
0, 1.
0, 1, 2.
Yeah, but
Actually,
it's next to
Yes. Okay, so the fixed point actually okay, they satisfy the equation of, where is it? 2x equal mu plus x squared, right? So this is actually x squared minus 2x plus mu equal 0, and that means that critical point, let's do it plus minus, is 2 plus minus 2 plus minus square root of 4 minus 4 mu over 2, and this is 1 plus minus square root of 1 minus mu, right? Okay, that means that we have fixed point of 1 plus minus square root of 1 minus mu, and 2 plus minus 2 square root 1 minus mu. Right? Those are the two critical points. Right? Great. Okay, so first it is easy to see that we have the critical value for mu, right? That is, for mu is 1, right? Okay, and this is actually the point where the bifurcation will occur. Let's look at the Jacobian. So we have where is it? Here. Okay, minus 2, 1, and 2x and minus 1. Right? Okay, so let's look at the fixed point. Okay, we have minus 2, 1, and okay, let's write it like this. Okay, so from here we can see the trace is minus 3, okay, lower than 0, right? And the determinant is 2 minus 2 x star. Let's write it here. 2 minus 2 x star. What does it mean is 2 minus 2 minus plus 2 square root of 1 minus mu. Right? This is minus plus 2 square root of 1 minus mu. Okay? Okay. So, for the plus point, we get tau lower than 0 and delta also lower than 0. Okay, so we have saddle node. Okay, and for minus, so we get tau lower than 0, but delta lower than 0. Okay, So now we need to find, is it a spiral or a stable node? Okay, how can you know that? So we'll look at the, where is it? Here, the determinant of t squared minus 4 delta. Okay, so this is, tau is minus 3, so 9 minus, we are at the minus point. Okay, so we have the plus. So minus 8, 1 minus mu. Okay, so when it will be bigger than 0. If it is bigger, we get a node. Okay? If it will be lower, we got a spiral. Okay? So when it happens, so let's look at minus 1. Let's talk about this area. Okay, so we get mu is lower than 81 minus 64 over 64, and this is answer with minus 70 over 64. Okay, so for mu lower than this, we get stable node, and for mu lower than this, we get stable spiral. Okay? Cool. So see, let's sketch it. Okay. So how much areas we have? We have first mu that's lower than, where is it? What did we have? First mu lower than minus 1, right? Then mu between minus 1 to minus 70 over 64. Then mu between minus 17 over 64 to plus 1. Wait. Plus 1, what I missed? No, 270. 2, no, I missed something. Between no, yes. No. Minus. No, I'm fine. Okay. Between these two, 1 and mu lower than 1. Okay? Mu lower than 1, we have a okay, we have a stable spiral and a saddle node, right? So we have, let's look at this. We have at okay, let's look just at plus and minus. Okay, we have those 2 points. Here we have a node, okay, and here spiral. So we have something like this. Okay, between, okay, let's do it more. Okay, between minus 1 to minus 17 over 64, we have node and node. Okay, so here we have this, and we suggest things going like this. Between minus 17 to 1, we have, no, okay, it's actually the same. Let's look at the critical point. Okay, this is what we care about. We have now 1 point, right? Half stable. Looks like this. Okay. There is something like this, and here things going there. Okay. Like okay. Some flow this way, and for mu bigger than 1, we have just flow. Okay, without the critical point. Okay, cool. Okay. And next, okay, consider the Weis-van der-Pol oscillator x d dot plus mu x squared minus 1 x dot plus x equal a. Find the curves in mu a space at which of the bifurcation here, up here. Okay. And so first let's define y as x dot. Okay, so we have y dot equal to a minus mu x squared minus 1 y minus x. Okay. Okay, we can easily see that we have a fixed point at a 6 0, right? Or let's write it like this: x dot equal y. Here it will be 0 just if y is 0 0 a minus x. Okay, this is the fixed point. Okay, the Jacobian will be 0 1 minus 2 mu xy minus 1 minus mu x squared minus 1, and this is at the fixed point 0 1 minus 1 and minus mu a squared minus 1. Okay? Okay, let's find the eigenvalues. So we have lambda minus 1 1, lambda plus mu a squared minus 1. This is lambda squared plus lambda mu a squared minus 1 plus 1 equal 0. So we get lambda plus minus with, let's call it c. Okay, so this is equal to minus c plus minus square root of c squared minus 4 over 2. Okay, so Hopf bifurcation, when we will have it? When we have an imaginary an eigenvalue that have also an imaginary part and a real part. Okay, so the imaginary part, first we want an imaginary part. Okay, so we want c squared minus 4 lower than 0. Okay, what is c squared? It's actually mu a squared minus 1 will be squared lower than 4, so we have mu a squared minus 1 between minus 2 and 2. Okay, first. Second, we want the real part to cross the axis. Okay, so we want minus c. This is actually minus mu a squared minus 1. Okay, we want this to cross the 0. When it will happen? If mu equals 0 or a equal plus minus 1. Is this exist this? Yes. And this also. Fine. K0 is between minus 2 and 2. So we have half bifurcation at this. Okay. Okay. Last exercise. For the system, r dot equal r mu minus sine r, and theta dot is 1. Discuss the bifurcations as m as mu varies. Okay. Okay, first we have theta dot is a constant. Okay, so we know that the system is just going counterclockwise. Okay, and all the system will be depend on r dot. Okay, so let's look at this function. I should look for different mu. Okay, so first, if the absolute value of mu is bigger than 1, that means that r dot is bigger than 0, right? All the time. I'm sorry, no. This will be bigger than 0. That means that r dot equals 0 just if r equals 0. Okay, cool. Now, if mu, where am I? Here. Okay, if mu is lower than 1, that means that r dot is also lower than 0. Okay, always. Because this is positive and r always positive. Right? And if mu is lower than minus 1, this is still on this area, so r dot is lower than 0. Right? Okay. So here we will have a spiral stable and here an unstable spiral. Okay, cool. Okay, for mu, for absolute value of mu lower than 1, what we have? So first we have, of course, this point, right? It still happens. And we have also a lot of another stationary points. Okay, we'll have like something like this. Okay, many points, stable and unstable in order. Okay. Okay, this in this region we have also the edges. Okay, from mu equal minus 1, we will have like this. Okay, this is all the half. Okay, and from mu equal 1, we have the opposite. Oh, I'm sorry, it is. Oh, never mind. Let's just. Maybe it's this one. Okay, and here we have like this. Okay, all the Okay? Okay, cool. Okay, so what do you have until now? We have for absolute value of mu, r equals 0 is stable or unstable spiral, right? And between -1 to 1, we have a lot of critical points, right, that appear and disappear. That means that we have a lot of of saddle node, right? We have many saddle node bifurcations. Okay, this is called saddle node bifurcations of cycles. Okay, because it's like on many radiuses. Okay. How it looks like. So it actually, okay, if we have mu is lower than -1, what we have a stable spiral, right, 0. Okay, for mu lower than 1, we get again spiral, but unstable. Okay, and between them, what we have the r equals 0, and then many cycles. Okay, that actually do this thing. Okay, going inside and outside from the cycles. Okay, this is called again saddle node bifurcation of cycles. Questions? Okay, so we finished.
תגיד, המבחנים של עוזי, הם קשים של חבורות?
לא בין, כאילו, לא,
בין שאלות